Okay, so welcome back, and the first of the last two talks, and we're very happy to have Shinpei Baba, and he's going to talk about holonomy representations of CP1 structures.
Okay, thank you, Subhojoy, and yeah, thank you, and thank organizers for inviting me here. It's been very wonderful here. So there's a note from Francois Labourie, which I cannot erase till he give me a permission. So anyhow. So this is a collection from his lecture, and then so I will talk about CP1 structures, which we have seen in Stefano's talk, and kind of relate to Ken Bromberg's talk, and yeah, also Bertrand Delaw's talk. So let us recall. Okay, good. So let us recall one of the theorems which Stefano stated. So let S be a closed, orientable, or say oriented surface of genus with 2. Then theorem that, can I say, homomorphism from the fundamental group for this surface into PSL2C is a holonomy representation of some CP1 structure. So that's a complex projective structure. So I call it, they call it complex projective structure, but I write CP1 structure. CP1 structure on S, if and only if the following two conditions holds. So the first condition is that image of this representation is non-elementary. We will recall this meaning, but just it means this representation. Okay, so this is called law. Law doesn't degenerate this surface group too much. Okay. And second condition is that law is originally a homomorphism into PSL2C, but it leads to the double cover of PSL2C. So phi 1 of S to SL to C. Okay. And moreover, okay. So just so those conditions are algebraic conditions, and that which characterize being holonomy representation of CP1 structure. Okay. And then I think if moreover, if the second condition fails, then rho is a holonomy representation of some CP1 structure on S with a single branch point of degree 2. So we need to have a one branch point to be the holonomy. Okay. So let us recall. So we quickly recall the definition of CP1 structure. a CP1 structure is in a C1 PSL to C structure. So it's a maximum atlas modeled on CP1. So locally open sets, locally open set of CP1, and transition maps is in PSL2C. Okay? As PSL2C is or biholomorphic maps of CP1 acting by linear fractional transformation. And it's up to isotopy of surface. So a CP1 structure in a pair. Structure S is in a pair of the developing map, which is local homomorphism from the surface to CP1, and the homomorphism from the fundamental group of surface into PSL2C, such that F is so equivariant. And F is called a developing map. And then rho is called the holonomy of the CP1 structure. And then everything is up to PSL2C such that its pair is equivalent to conjugation on rho by some element in gamma, so some element gamma in PSL2C, and then post-composition of the developing map with this gamma. Also recall that each CP1 structure has a complex structure. Just bring back the complex structure of CP1 by the developing maps. Okay. And then with respect to the complex structure, this branch point looks like a simple zero. Okay. So Stefano said like its branch point is locally looks like z goes to the z to the n. Topologically, the branch point, and then with a complex structure, like it's being being degree 2 means just it's a simple zero, at most simple zero. Okay. Okay, so people probably get tired by now, so let's start with something easy. Even start with torus. Okay. So the plan is just to I have 2 lectures. So first lecture I do some background, and then sufficiency. Oh no, necessity. We show that those conditions are necessary, and then second lecture. Which is more, which is the meat of the proof, which we actually construct, giving a representation satisfying those conditions, and construct a CP1 structure with the holonomy. So we show that those conditions are sufficient. Okay. Example, CP1 structure on torus. Actually, let's tell them that. Oh, did I write the name here? Okay, I forgot to write. So this the main theorem we are discussing is due to Garo, Kapovich, and Marden 2000. So it's not a new theorem, but recently it's being used quite often. So it's good to know the theorem, I think. Theorem is that every CP1 structure on not T1, T2, we are on surfaces. On T2, on torus is now how can I say C complex affine structure. Okay. This is due to, I think, Gunning. Just instead of looking at the old linear fractional transformations of this form, so this is an element in PSL2C as an action on CP1. We just look at the one affine transformation, C plus B. AB are complex numbers and A is not 0. I think the point is that the fundamental group of torus is C cross C, which is abelian, so there's a quite strong restriction on what kind of holonomy CP1 structure take if it's on torus. Already wrote examples, so in particular Euclidean structure. We just take Euclidean structure, just generated by two translations. So Z goes Z plus B and Z goes to Z plus C. So that those translation directions are linearly independent. So if you quotient complex plane regarding it as Euclidean plane by the Z cross Z generated by two translations, you get Euclidean torus. Okay. So in this case, developing map is embedding onto C, and then the holonomy representation takes generating set of fundamental group of T2 to those translations. Okay. So here we have holonomy representation and developing map for Euclidean torus. And if you have this, you can compose with exponential map. Now, so this parallelogram is the fundamental domain of the Euclidean structure, but this fundamental domain becomes more like a fan-shaped region. Image is not necessarily embedded, but only immersed. But so by this I mean that you compose this developing map for Euclidean structure onto C with exponential map, and then taking, what can I roll? So what am I doing? Exponential map is low. So by this I mean originally holonomy is a translation by some complex number, and this goes to dilation by the exponential map, exponential of this translation vector. And actually, the theorem of Gunning tells that those two are only examples for CP1 structures on torus. It's quite, for torus case, it's quite simple. Okay? Although you need to, there's something to prove. And the holonomy representation of this kind of things are elementary representations. Okay? So let me define. One of homomorphism from the fundamental group of surface into PSO2C is elementary if its image is elementary subgroup of PSO2C. Namely, if image of rho fixes, there are two possibilities. Fixes a point in the Riemann sphere, or CP1 is bound in hyperbolic space, so this fixed point might be in the interior of this hyperbolic space, or image of rho preserves two-point set. What? Just say 2 points as a set. So the second case, the image preserved 2 points in plural. So after composing exponential map, this holonomy preserves 0 and infinity. Okay. In this case, it's fixing a particular point. I mean, both points, point-wise. But then a priori, there are also representations that switches 0 and infinity. So those are elementary representations. And then the first example fixes a point at the infinity. Okay? And homomorphism is non-elementary otherwise. Okay. Equivalently, what can I say? Because in the theorem, the condition is that rho is non-elementary. Let us see in a slightly different way that, as Bertrand kind of said it, so that image of rho is strongly irreducible and image group is non-compact. So PU2 is sitting in PSO2C. So image can possibly be in this compact subgroup. And strongly irreducible means that it's irreducible. Every finite index subgroup is irreducible. Is everything okay? Okay, so let us look at the lifting property of the holonomy representation. So each CP1 structure, so this is CP1 structure on the surface S, and it corresponds to each CP1 structure has a complex structure. And then from the developing map of the CP1 structure, we have a holomorphic quadratic differential. On this Riemann surface X. So holomorphic quadratic differential is locally well-defined holomorphic functions with some compatibility condition under the transition maps. Okay. So this CP1 structure is a pair of the developing map and holonomy representation. You can take C Schwarzian derivative of the developing map given by the following formula. Taking derivative of the developing map, second derivative, and then just apply this formula, okay? Which appeared in Ken Bromberg's talk. I don't remember if he wrote in this slide, but. So anyway, from the developing map, you can cook up a nice holomorphic function on the Riemann surface. Just fine. Am I missing something else? Oh, the variable. Okay, this is okay. Do that right. Thanks. I need to put that here. Are there any other typos? Maybe one more parenthesis here. And then you can go backwards, that if you have a Riemann surface and a holomorphic quadratic differential on the surface, we can make a CP1 structure. So we solve Schwarzian equation. So regarding universal cover of the this Riemann surface as upper half plane, as it's biholomorphic to it. Double prime T 1/2 is differential. Oh, not fine. Our parameter is Z, so maybe put it Z. Z equals 0. Okay. So U is this exterior to C. So solve this second order linear differential equations, and we get two answers, two solutions, two linearly independent solutions, U1, U2. From X tilde to C. And then by change of, let us look at the action of fundamental group U1 C, U2 C. And if you change this point C by the deck transformation, so we get a matrix here. And you see, it's non-degenerate. Just because we are solving basically the same differential equations, just changed by the deck transformation. Then we have a flat C2 bundle over the Riemann surface X. And then by projectivizing, we have the developing map. 1, U2. Just take the ratio of those two solutions. We have a map, holomorphic map from upper half plane to CP1. And then projectivizing this matrix, we have the holonomy representation of the surface group into PSL2C. Thus, this holonomy representation lifts to I1 of S into SL2C. But it's came from the projectivization. Yeah. And there's also corresponding holomorphic differentials for branched case, and then you can also see that if representation, the holonomy representation of CP1 structure with single branch point does not lift to SL2C. Branched case, so this is degree 2 branch point. One need to think that differential of this form Again, solving the Schwarzian equation. We have two linearly independent solutions of the following form. So starting with c to the 3 halves, and then smaller terms, and c to the minus 1 half with smaller terms. And then if you look at the monodromy of the branch point, if you take a peripheral loop, or a loop going around this branch point, and then if you look at the monodromy from this solution, one can see that monodromy is minus identity. Okay? So, how can I write this? Okay, anyway, monodromy is of this form. To see the lifting property, you need to see that. So take a standard generating set. And relator is the product of commutator. Because of the monodromy around the branch point, if you try to lift this representation, this relator must go to -1, which shows that you cannot lift the representation. Okay. Look at the deformation space. CP1 structures. So we have it's denoted by P. Base of all CP1 structures. On surface S up to isotopy. And this is a vector bundle over Teichmüller space. So this is all complex structures on the surface, again up to isotopy. And then fiber over a Riemann surface is the space of holomorphic quadratic differentials. As this space of complex structures called Teichmüller space is diffeomorphic to Euclidean space of dimension 6, G minus 6. So G is a genus of the surface. So I think from now or from somewhere, I've been assuming S is in the theorem, so it's close-oriented surface of genus at least 2. Okay? And then fiber is a complex vector space of dimension 3g minus 3. Thus, deformation space is diffeomorphic to Euclidean space of (6g minus 6 times 2). We have a we have the holonomy map. From this deformation space to the character variety space of representations, taking a CP1 structure to its holonomy representation. And the character variety chi is the space of homomorphisms of the surface group into PSL2C. Up to PSL2C. This is roughly up to conjugation. And it's a little bit stronger equivalence class, but just to think about CP1 structure on a closed surface, yeah, I mean, some of this equivalence class is enough. What I'm missing? Oh, inverse is here. Okay. And the gamma is in PSL2C. Are there any other typos? We have affine algebraic variety, and yeah, we have a nice projection, very simple projection map. It's known that this holonomy map is locally biholomorphic map. But it is not a covering map. Onto its image. So locally biholomorphic means, in particular, it's local homomorphism. So somehow local correspondence by the holonomy map is quite nice. However, it's not a covering map onto its image. So a lot of questions about CP1 structures or more general geometric structures are to understand nice properties of this holonomy map. Okay, so this is due to Hetchau, I think, in 75, and biholomorphic part is, I think, R and Hubbard. So in particular, the theorem we saw at the beginning tells the image of this holonomy map. Okay, like The domain of the holonomy map is data analytic object, Riemann surface, and holomorphic quadratic differential, and then target is something quite algebraic, and then the main cell tells the algebraic condition for the image of this holonomy map. Proposition. Suppose that this is a closed surface of genus at least 2, as before. And let C be a CP1 structure on S, then its holonomy representation is non-elementary. Okay, so we show that one of the conditions in the main theorem is actually a necessary condition. And I think Bertrand stated this statement, but we can look at its proof. Okay. Oh. Maybe I should say a little bit more about, before that, maybe I should say a little bit about this holonomy map that, because entire holonomy map is quite somewhat complicated. It's not a covering map onto its image, but if you restrict it to, okay, let me go back here. If you just look at fix a Riemann surface, and if you restrict to this holonomy map to all CP1 structure on this Riemann surface, okay? This is the proper embedding. Into the character variety. Okay. It's quite, you get, and this guy has half dimensional. You get a half dimensional slice in this character variety. Okay. And I guess embedding, injectivity is, I guess, due to Poincaré, and properness is by, I think, Kapovich, also Tanigawa. Okay, but different proof using extremal length, and also David Dumas give another proof using Epstein surface. So we saw Epstein surfaces in Ken Bromberg's talk, but point is that when you scale the differential by large scalar, like you can kind of see like Epstein surface pretty clearly, and then you can see the properness. You can, so when you scale this differential by large number, you can see that its holonomy representation also diverges. Some translation length gets really, really long. Okay. Any questions? Proof. So we show this by contradiction. So suppose that this representation is elementary. Then there are two cases that either rho fixes infinity or it preserves 2 points. One more case. Two rho fixes a point or image of rho is bounded. Bounded subset in PSO2C. The first case, so we can assume those 2 points are 0 and infinity of CP1. So look at the inverse image of those 2 points, 0 and infinity, and then remove from the domain of the developing map, which is the universal cover surface, then quotienting out this. So we have a discrete points removed from universal cover, but those points are invariant by the deck transformation group. So we have by quotienting out, we have closed surface of genus at least 2, S with possibly some points. Finitely many points are removed. What are the finitely many points? Oh, just you take inverse image of those 2 points, and then because developing map is local homomorphism, inverse image in the universal cover it's a discrete sets, and then by the equivalency those points, this is also Pi1 invariant. So you can quotient out. Okay. And then we start with this in a closed surface. So this inverse image descends to finitely many points. Yeah. To be precise, like I'm using that fact that developing map. Huh? Okay, I'm not using that anymore. Okay, that. And then in this case, image rho is contained in what's this? Just dilation. Okay, so see. Oh, a little bit more maybe, but okay, because my exchange is 0 and infinity, but anyhow, how can I write? Stabilizer point. The subgroup which fixes 0 and infinity. And then CP1 minus 2 points. has a complete Euclidean metric. Invariant under this stabilizer. So this metric is just pushing forward the Euclidean metric of the complex plane by the exponential map. Thus, this surface minus finite many points gives a complete Euclidean structure, and this is a contradiction to the Euler characteristic. Any question? There's a natural structure on that CP1. Oh, so this is infinity. Okay. To be precise, I'm using the fact that the developing map has a path lifting property away from the limit set of the group. I should write. Here I'm secretly using for the completeness. So if this developing map has a path lifting property. In the domain of discontinuity. So somehow, I don't know. So limit set is, so this domain of discontinuity is CP1 minus limit set, and then here limit set is you take a point in hyperbolic space and you look at the orbit with this point, and then take a closure in its city with its ideal boundary, and then looking at the intersection with CP1. Okay? So it's kind of like attracting points. And then somehow this local coordinate does not really get small unless it's near the limit set. So that's basically why you have the lifting property. Yeah, coordinate chart doesn't get really small away from this limit set. And this is actually used. So Stefano's talk, you saw like Goldman's theorem about CP1 structure with Gaussian holonomy, such that every CP1 structure with Gaussian holonomy is obtained by grafting hyperbolic structure, very standard one. And then he's actually using this theorem to show when you decompose the surface by like subsurfaces, yeah. By putting back the limit set, which is a circle, you actually need to use this theorem. And Bill doesn't actually, he used it, but he didn't prove it, this theorem, and maybe proof appeared, I think, good difference. I saw it, I think, Sartan's paper, possibly with his collaborator. So anyway, this is used for the completeness here. Second case, that rho fixes a point. By rho, I mean like image of rho. Everything's image, this image group. So we can assume this point is point at infinity. That means this holonomy representation is in the affine maps. Okay. And then we can do somewhat similar way to the way we saw for the first case. However, there's no invariant metric on the complex plane preserved by this affine maps. But then here, like this point is that this set of affine transformations preserves parallel lines on the complex plane. Okay. Parallel lines, straight lines, stay parallel by these transformations. So, so you look at the same. You look at the again the same thing. So universal cover minus inverse image of this point at infinity, and divide by the Dick transformation. This is possibly some points are removed from the original surface S. And then, what can I? And then we have a notion of like a parallel line here. And then you can find nice fundamental domain using the straight line on here. Basically, you can still use the Euler characteristic argument, but just using like nice fundamental domain, like some sort of yeah. Nice. Polygonal. Fundamental domain. And then from here, you can calculate the Euler characteristic. And then reduce the contradiction. I think you can show that Euler characteristic of this surface with some point removed must be non-negative, which is a contradiction. Non-negative, and this is a contradiction. And third case is easier than this, just sort of, so image is bounded, means that this image is contained in U2. And you can regard this as isometry group S2. And then you can pull back the spherical metric to the domain S, and then you can again reduce the contradiction. Without removing any points. Okay. Any questions? Let me look at one more example of CP1 structures. Coming from a Schottky group in PSO2C. So it's kind of like a generic type of free group, discrete free group sitting in PSO2C. We just need a rank 2 case. we take 4 disjoint disks. They don't need to be round, like a round disk, geometric disk, but then, I mean, you can assume it's not too important for this talk. D1, D1 prime, D2, D2 prime. Then it's rank 2 free groups, so you take a generating set. Gamma I takes interior of di to exterior of di prime. So gamma 1 pushes 3 disks into this disk. You can, the similar thing happens for gamma 1 inverse, and then you can see by this action generated by those 2 elements, you see Cantor set as the accumulation point. By quotienting out the domain of discontinuity, which is the limit of the complement of the Cantor set by the Schottky group, we get the genus 2 surface, whose fundamental domain is here, the complement of those 4 disks. So that the boundary circles appear somewhere around here. In this example, so this is a CP1 structure on genus 2 surface. And then its developing map is a covering map. Onto the domain of discontinuity, the complement of the limit set. And then holonomy representation, rho takes those orange loops, which corresponds to the boundary components of those disks. We started with 2 identity, as it's coming back to the same point. And then corresponding to the generating set, those loops maps to those loops goes to generators, corresponding generators. Okay. How much time we have? Oh. Okay. Let's retalk. And from here, you can cut into 2 pair of bands. For example, taking 2 parallel lines, not parallel lines, but taking those red loops and then like union of those two loops. And they have different orientation, opposite orientations. And the good thing about cutting it here is like originally it's first like pair funds are really nice surfaces which are good for constructing closed surfaces, and we will indeed use it the next time. And then moreover, like here, we are after cutting around the loops on those pair funds like holonomy representations. So those CP1 structures, they're holonomy representations. Isomorphism. Onto the Shoki group we started with. And here, there's many choices for cutting this closed surface into this type of pair bonds. Namely, you can then twist. You can take here. We took those three loops, but we can then twist those loops along one or two of the orange loops. And still, because we are twisting along a trivial loop, in terms of its holonomy, it doesn't change the holonomy representation. Okay? I still have 4 minutes, so let me just a little bit outline the proof for the opposite direction, and then we actually do the proof in the next lecture. So, well, at least outline the more details of the proof. So we have the sufficiency. So we want to have low fundamental group of surface into PSO2C. This is non-elementary. Then we decompose. So a priori, this can be quite complicated representation. Image might be dense in its image. Okay. Then first find multi-loop which such that multi-loop M such that S minus M, the complementary components are pair bonds. And if you restrict the holonomy representation, I mean the representation you started with to fundamental group of each pants, pair pants, called P, is now isomorphism onto a Shoki group. For each pair of pants. And then from there, you can, okay, so you have, you can construct like in this way, you can construct a projective structure on pair of funds. In this way, and you glue them together to realize a CP1 structure with this holonomy representation. Okay. The main point is that so originally, like this representation is quite complicated. Okay, doesn't need to be discrete at all, and then it's kind of hard to make CP1 structure associated with it, because a lot of example we saw is just finding by quotienting like a nice domain sitting in CP1 by discrete free group. Okay, so we decompose. So the main task here is that just finding a decomposition. This a priori quite complicated composition to nice discrete groups. Okay, and we see any other comment. Okay, and we see more detail next time. Okay, and I stop here for today.
So thanks, Shinpei, for a good talk. So who's and any questions? Anybody has any questions? If not, let's thank Shinpei again. And tomorrow we'll meet at 9:45 in the morning for the last talk of Shinpei.